Hey, hello all. My name is Hassan Haram, and I am about to present to you the paper of optimizing ADWIN for steady streams. The other authors are Ahmed Awad and Hassan El-Kafrawi. There has been some collaboration between Tile University in Egypt and the University of Tartu in Estonia. So for our introduction, as we know, the data is enlarging day by day. As an example of this, our interactions through IoT devices such as our cell phones, laptops, smart cars, etc. Most of the interactions is instantaneous, which gives room to online machine learning. Data stream analysis suffers from a change in data distribution, such as a change in user preferences or varying weather conditions or economic changes. This change affects the prediction accuracy of the machine learning model, and this leads to misled results. This change is called a concept drift. So we need to be able to detect this change in data stream. And for this, we have three main classes for detectors used to capture this change. The first class is statistical, the second is window-based, and the third is ensemble-based. So we have chosen ADWIN as our detector because its real-world capabilities in data streaming and also its open source in MOA, which is the largest data frame for data streaming. There has been development to ADWIN enhancing its performance, especially latency and the throughput. And this development produces three variants: serial ADWIN, half-cut ADWIN, and the optimistic ADWIN. So for our challenges, we have two main ones. The first one is compared to the original ADWIN, where we need to see how much its variants are superior. So we have evaluated them in terms of accuracy, throughput, memory consumption. The second challenge is how ADWIN and its variants behave with state stream having distance drifts or no drifts at all. So starting with the first challenge, so for the evaluation, we use both synthetic and real-world datasets. We compare ADWINs, as we have said, in terms of accuracy, throughput, and memory consumption. We have different values of ADWINs in Delta, which is the only configuration of ADWIN, which is the sensitivity of detecting a drift. This is as an example of a synthetic stream. We can see the effect on the incremental dataset. So compared to the original ADWIN, we can see that serial ADWIN and half-cut ADWIN both have the same accuracy and the internal window size, while the optimistic ADWIN has latency and less accuracy and higher internal window size. Here we can see similar results when applying ADWINs on a real stream, which is represented in the airlines dataset. When we test ADWINs on a state stream, we can see that all ADWINs have the same behavior, detecting zero drifts while dropping no elements, which may exhaust our resources. So for our conclusion of evaluating ADWINs, the optimistic ADWIN has worse performance in terms of accuracy. For the half-cut ADWIN, it has less throughput, and for the serial ADWIN, it improves the throughput while maintaining the accuracy. So we can say that it's a best ADWIN variant. So moving to our second challenge, as we have seen, ADWIN and its variants don't behave well with steady streams. We can see that ADWIN only drops elements when it sees a change. Otherwise, its internal window size keeps growing. For our new ADWIN plus, it keeps only diffused sufficient elements to see a drift and drops the rest, which saves our resources and enhances the overall throughput. So for our experimental setup, we use the same as our first evaluation of ADWIN. In addition, we add more datasets which present some variants for the synthetic dataset to see the behavior of our new ADWIN on different states of streams. And for the configuration, ADWIN plus have 5 parameters to assign, so we have different configuration. Here we can see the effect on a steady stream, almost 80% less in memory consumption for a stream containing any drifts. We can see that our new ADWIN still saves memory compared to the baseline ADWIN. We can see this in the red curve versus the blue one. Also, green and orange curves, they visualizes more memory saving, but at the expense of accuracy. For streaming containing a number of drifts, we can say the same as the previous state while more maintaining the accuracy. Here for a stream containing low number of drifts, which is almost steady, we can say the same as a steady stream state. Also, when we experimenting on real stream, here we can conclude the same result as on the synthetic dataset. So for our conclusion, we can say that ADWIN plus almost save 80% of memory consumption when the stream gets steady, maintaining the accuracy and enlarging the throughput, but it's sensitive to its configuration, and this may affect the accuracy. So for our future work, we need to dynamically change its configuration as a function of the stream state. Of course, if you want to explore more and more about our results and datasets and also our source code, you can always check the paper and those GitHub repositories. And also, if you have any questions, of course, I am happy to answer them all. Thank you.